1. Section 3.8, implicit differentiation. It's one of the necessary techniques of differentiation, of differentiating. You might not always have an explicit form. You might not always have a function. So there is this method that helps us, which utilizes chain rule, to differentiate even those relations which are not functions. For instance, if I look at something like y equals x squared plus 3x, plus c to the x, it doesn't matter. This is solved for y, and we know it's a function of x, and this is explicit. But there is something like this, x squared plus y squared is equal to 9. What would that be? Exactly, circle with radius 3. Very good. Is that a function? Not a function, right? And cannot be solved for y. You can solve and get plus minus square root of, but again, it's not a function. So we will call this implicit form. Implicit. Now, I said on the first day that calculus is the calculus pays attention to functions. We covered the definition of a function. It was there on the test. It might be there again on one of the exams. Function is a rule which assigns to each x in the domain a unique y in the range. And I said that calculus is done on functions. Now, circle, and I've been practicing circle a lot. Oops. Well, I will draw a circle. No, I'm amazing with these things. So as you take a look at the circle, you can still find the tangent line at this point. Now you have a tangent line, and the tangent line, that looks like pi, tangent line, there we go. The tangent line will have a slope m, and that m has the derivative at this point. So there has to be a way to find the derivative, even though this line does not represent a function. So this is where implicit differentiation jumps in. Proofs and derivations, again, aside. Do that in Janusz class. We look at the procedure to find this. And the procedure is very interesting. You get to take the derivative of the equation as is, except every time you take the derivative of y, you will have to follow with the chain rule dy dx. Some of you would like to put y prime, whatever. So procedure is to take the derivative. I want to find the derivative of x squared plus y squared equals to 9. Now I have to go into the new line because it's already equal sign inside. So derivative of x squared is? Very good. Derivative of y squared is? What is it? 2y dy dx. Very good. And derivative of 9 is? Thank you. After such a long pause, derivative of 9 is 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, and then finally, boom, 0, right? See, this is, sometimes I really feel alone in a classroom, like 25 people. You know, then depression and everything else kicks in. The derivative of 9 is 0. Hey, for all 5 of you. All right. Yeah, stream, there's actually no one in the classroom. It's just... all we need to do is to fish out dy dx equal everything else. And we're done. So now algebra. So procedure is very simple. Take derivative term-wise. Every time you take the derivative of y, follow with dy dx. And then fish out dy dx. That's all it is. So 2x is equal to negative 2y dy dx. Divide by negative 2y on both sides. So dy dx is equal to 2x over negative 2y. And finally, derivative dy dx is equal to negative x over y. And that's the answer. Observe that the derivative of circle is always negative x over y, regardless of the radius, because radius gets annihilated by the derivative. No matter what you put for the radius, whether it's 9 or 25, well, 3 or 5 or whatever, the derivative will always kill it. The 2's will always cancel, because x is squared and y is squared. So the derivative of the circle, regardless of the radius, is always negative x over y. Now that you know what your derivative is, you can find the tangent line, and you can do all of these other things. Fair? Awesome. You are going to run into many problems where you cannot solve for y, which creates it into an implicit function, which means you will use implicit differentiation. Example number 2 might be xy cubed plus sine x is equal to cosine y. Whatever you can come up with. It really doesn't matter. Does anyone see anything interesting going on in this problem? Multiple y's, awesome. What else? Multiple x's are a standard feature. You look like you want to say something, but you are holding it back. Product rule, very good. First term is the product rule. Awesome. It's a function x times y cubed. So the first term has to be taken care of by product rule, making sure that anytime you take the derivative of y, you follow with a chain, dy dx, and then the rest you take term-wise. So you will have 1, 2, 3, 4 terms at the end. Awesome. Term by term, product rule is first. Copy the first, derivative of the second. Yes. You are going to have full dy dx, which you have to pull together through the magic of factoring, and then isolate it to the magic of division both sides. And fix the row above. Fix what? The row above dy dx. It's a completely different thing. With the dxy, you find the slope of the another one. So I have to put it here. All right. So you suffered enough. Let's do this together. The first term is the product rule between x and y cubed, which means, here I'll put the red dot there, it's a product rule, which means that I'm supposed to do the product rule. Copy the first, which is x, take derivative of the second, which is y cubed, that would be 3y squared, and because I took the derivative of y, I follow with dy dx. Plus, copy y cubed. I do not put dy dx here because I did not differentiate it, I just copied. And then times derivative of the first, derivative of x is 1. Plus, derivative of sine x is cosine x, and derivative of cosine y is negative sine y. I was taking the derivative of a term which had y, which means dy dx will be there. So this is our first stage. Now, we are supposed to fish out dy dx and have dy dx equal everything else. Now, we have two terms with dy dx, which means the only chance of doing this is to put those two terms on the same side, factor it out, and then divide by the extra. So 3xy squared dy dx stays on the left, and we bring plus sine y dy dx from the right to left, and ship the other two terms to the right side because we don't need them. They don't have dy dx. So I rearrange the terms so that all the dy dx terms are on the left. At which point I factor out dy dx, and we have 3xy squared plus sine y equal to minus y cubed minus cosine x. Divide both sides by what we don't need. And there we go. There's the derivative. Cool, right? So all it's left to do is to do the implicit differentiation with chain and quotient and chain rule and product rule and all in once, right? This is called implicit differentiation. Now I'm going to work on a much simpler problem to bring something across, a point across, and then maybe you will start understanding this better. We are moving towards one of my favorite sections, 310, which is the word problems application of this lecture. So hopefully what I'm going to write now will clear things a little bit, at least for the future. At one point I will talk about dimensional mismatch. Right? We'll figure out what that is. But I want to start first with the idea of variables and parameters, and then when we take derivatives, what's happening at the core, so that application later on is easier. And we're going to do a very simple problem. So first of all, I will call attention to our notation for derivative, which means this as well, because this notation comes from here or from here. If you can all see this as a one big same mess within Leibniz notation, you are already solving half of your issues, because that y is actually f of x is actually the function that we are working on, in this case in particular x to the fourth. So no matter which one of these notations I use, they all portray the same thing, which is the differential operator, which is like an instruction. This is the instruction. Instruction says take the derivative of this. So understand the instructions, license and registration, right? That's the instruction. So the instruction is take the derivative. Once you have that, you have to take the derivative of something, and then you get the answer. Now, I will write down a new problem now, which will say the derivative, take the derivative of, let's go with a to the x plus x squared, okay? And I'm going to write something. A to the x dx over dx plus 2x dx dx. Now, you haven't seen me write this before, ever. And we should all agree immediately that dx divided by dx is 1. Right? But that chain rule, which I never wrote before, is not needed because it always reduces down to 1. But it plays an important role. It says, I took the derivative of x in respect to x, which means that x is the independent variable, the main variable of the problem. So one more time, this over here is a chain rule that was there for every single problem we wrote so far, not in chain rule, but since the beginning of the differentiation, in 3.1, all right? Anytime you took the derivative, this dx dx was supposed to be there. However, I didn't put it there ever because don't need it. Dx divided by dx is 1, and that never changes whatever is here. Same thing happens here. Derivative of x squared is 2x, followed by the chain rule, which says I took the derivative in respect to x. I took the derivative of x in respect to x. They cancel down, and you have your good old differentiation. Hopefully, this would make your implicit differentiation easier. Because now, with the implicit differentiation, I get to say, I don't know, e to the x plus square root of y, for instance, equals cosine y, whatever, doesn't really matter. So now we are going to take derivative term by term. Derivative of e to the x is e to the x followed by its chain dx dx, because you took the derivative of x in respect to x, plus the derivative of square root of y, which is 1 over 2 root y. Probably sick of this derivative already. Followed by its chain dy dx is equal to derivative of cosine y is, very good, followed by the chain dy dx. So how about you just remember that no matter which derivative you take, you always have to put a chain. Except when they match, they drop. You cannot have a composite here. If it's a composite, it might be a product rule, quotient rule, or chain rule. You will not have a situation in which you will have to put dx, dx, dy, dx in the same one, in the same term. Never. And now you see two implicit terms that you can put together and get the dy dx alone. Now, why would a story like this be important? Because related rates are coming up. And related rates, you are going to relate two rates through time. Maybe the volume and the surface area of the inflating balloon. Maybe the diameter of the sphere with the volume. Maybe you want to talk about the pressure versus the temperature in time. There's going to be a lot of cool applications. And these related rates will allow you to measure those things. Now, we are learning the mechanics of calculations, and then the word problems are the last section of this chapter. I believe 3.9 or 3.10, whatever it is going to be that lesson, which is one of my favorites. Further, talking about these derivatives and things, we discussed earlier what are the good and what are the bad notations for derivative. I did ask you not to use y prime. But I'm asking you that because of the purposes of applied. When you get to word problems and so on, your input variable x would mean distance, and input variable t would mean time, and you will have to be careful which one you're working with. not to confuse the two. If you put both of them together, then you are already in a three-dimensional space, or four-dimensional space if you take in consideration you have 3 dimensions, x, y, z, and then the time, t, that will be 4D, time space. Right, spicy concept. That's all it is, 1, 2, 3, 4. So I would like to write something. Y equals ax squared plus bx plus c. And now we look at this, and if you are using bad notation, this is what happens. Y prime equals 2ax plus b. Y prime equals x squared. Y prime equals b. Y prime equals 1. And at this point, you should be confused. You should be confused. Unless you are so super in mathematics and you'll say, oh yeah, of course, obviously, that's what's happening. But I'm using bad notation. Now, what do you think? I have a function on top and then 4 lines of derivatives. They're all first derivative. It's not like second or third and so on. So if you were to pick one of these to be correct, or 2 or 3 or all 4, which one you would be picking as a derivative?
As the whole term.
You would pick first one. How many of you would pick a second one along with me as a fearless leader? Thank you for your support. All 4 of these are correct. It's just that we have atrociously bad notation. And it's not clear. You are used to the fact that x is a variable. But why discriminate against A, B, and C? They can't be variables. They're not good enough because there is a beginning of the alphabet. Is that how we discriminate now? New Age. Right? Observe that the first derivative is the derivative in respect to x. What's the second one? Derivative in respect to a. The second derivative that you see there, the second, well, the third line, but the second derivative line, is dy dA. A is the variable, and x and b and c are all constants, and derivatives of those are zeros. Do we see that? Moving to the next one, b is the variable, and the other ones are constants and parameters. So what's the derivative? It's just b. Oh, sorry, not b, x. Wow. That just ruined everything. And the last one, derivative of c. So now I'm going to remove this awful notation of y prime, which hopefully you will never use, and just put the real notation there. This is dy where dx. X is the independent variable, which means that every other letter will be regarded as a constant, which means copy A as is, and derivative of x squared is 2x. Copy B, derivative of x is 1. And then derivative of c, which is a constant, is 0. Moving to the next line, dy dA. A is a variable, which means that x squared is a constant, also known as a parameter, which you can change. So the derivative of a is 1 because that's the variable, and then x squared just gets copied because that's the constant. A is a variable, which means b, x, and c are all constants. Derivatives of those are zeros, and they're gone. So we have dy dB, dy dC. This is the almighty Leibniz notation. it tells you what function was in question, and it tells you what is the main variable, what's the independent variable within that function, and you can take your derivatives properly. And now you're good to go. Unleash you upon the world, all right? When variables match, you don't have to write the chain rule. When they don't match and they are variables, you have to write the chain rule. So this story now gets changed when you say that multiple letters are variables. Multivariable functions will have more than one variable, multivariable, right? So say that you are talking, all right, everyone knows this function. It's like you go through the entire physics and chemistry, right? This is the one that you know on your deathbed. It's like, I don't know why. PV equals nRT, right? Anyone cares to share what this is? Ideal gas law, exactly. Also known the formula that works in your tires, all right? This is a constant here, so I might as well call this big K to make all simple. So I'll just say K is a constant. So we have PV equals to KT. Now, volume of a tire doesn't really change, right? But the pressure and temperature will. So you know that in the summer, because it's hot, and you drive, which is friction, so you put more hot on it, right? You should keep your pressure in a tire lower. Exactly. Right? Because if this goes up, temperature, this should go down to preserve this. You know, when truck drivers don't pay attention, you get those tires all over 78 on, right, in a shoulder lane. Much more of those right in summer than in the winter. So this is a multivariable function. One goes up, the other one goes down in order to preserve the equal sign. If you keep the pressure constant at high, volume is constant. When temperature goes up, it will push these two to go up. Well, the pressure can't really get any bigger, so the volume needs to get bigger and the tire explodes. It's a very simple physics. Very simple to understand these things if you understand mathematics behind it. Now, what's happening with these derivatives here? I can take the derivative in respect of any of these variables. And clearly I'm going to have a product rule on the left, because if we keep changing them all, pressure, volume, and temperature, you'll have the product rule. If volume is constant, let's say the tire can't expand, then in that case, you have the, you don't have the product rule anymore because V becomes a constant. So these are kind of analyses that you are doing, and you will know when you take derivative whether you have to follow with the chain rule or not. Another example, which will be looked in a detail later on at your related rates section, is a cylinder and a cone. When you look at these two shapes, they have very similar formulas for volume. It is base times height, and this one is 1/3 base times height, because it's what I call spiky object. So now, to derive the formula, base is pi r squared times the height, which is just age, and you're done. On the other one is 1/3 base is against circle, so pi r squared, and again times the height. Awesome. The two formulas differ only for 1/3, right? Yeah, geometry-wise and calculation-wise, if you are dealing with basic arithmetic and basic algebra, sure. Calculus-wise, vast difference. Imagine the water level rising over here. What's changing for the volume of water rising in here? Which concept is changing? Height, h. Is that a variable then? Yes, depends on where the water is, right? So age is changing, and because age is changing, radius is constant, pi is constant, then volume is changing. Cool, right? Get the water up here. What's happening? Radius is changing and height is changing, right? So when you take the derivative here, it's going to be the derivative of age only, but over here is r and h reciprocal. This one, much nastier than that one. But formula-wise, they look the same, right? So we have to be very careful with these types of analysis, and we do have the implicit differentiation to help us out with these calculations. And the rule goes like this. Every time when you take the derivative of a variable which doesn't match the independent variable, you have to follow with the chain rule. If you take the derivative of a constant, you get 0. If the constant is multiplied, you carry it over. So the same rules apply. The only new rule is that if you have dimensional mismatch, two dimensions on a 2D graph, x and y, x is your independent variable, y is the dependent variable. So two variable system. And when I find dy dx, I know that I'm looking for the derivative in respect to x. So when I have to take the derivative of y, I have a dimension mismatch. I am taking the derivative of y in respect to x, which is the reason why the chain rule piece dy dx survives. It's there. If I'm taking the derivative of x squared, then it's followed by dx dx. They cancel, and we don't have to worry about having the chain rule piece there. So this was a little discussion, more theoretical, on a theoretical side, and hopefully you understood some of it, because we are going to use this in our application later on in the section. Now let's take care of the few homework examples. One thing that you really don't want to see within these implicit differentiation questions is like sixth derivative of it, because like the first derivative is crazy enough, right? Imagine taking a second derivative of that, right? When this is your first, and then you have to take another derivative. So they progressively get worse and worse and worse. So maybe you do, one or two of those to just kind of feel the heat a little bit, and then we have software for it. Let's talk about examples from the textbook. Problem 8 says y squared plus 3x equals to 8. It says what's the slope at 1 square root of 5? So it's asking for the slope of the tangent line at 1 root 5.
this question, is it tangent t and then that minus that, or is it tangent and then the tangent of those?
But there are no parentheses, so
Okay, that was
right.
too much then.
Yeah.
Well, I will
Separate term. Oh, it wouldn't be. Well, yeah, it would actually. It would make chain rule. Yeah. So what's the derivative? What's what's the next line? 2y dy dx plus 3 dx dx, right? And then equals to 0. Good. Now, the magic. You actually don't have to solve for dy dx. You can just plug everything in. 2 times square root of 5. This becomes m plus 3. It's much easier to do it this way when you have multiple y's, dy dx's, sorry, to replace everything in instantly. M is equal to negative 3 over 2 root 5. We rationalize. I know, that's the tough one. And there's the slope. And then you can find the tangent line if you want to later. It's not a problem. Let's find the actual tangent line problem. Or something that is more interesting. Ooh. 24. Square root of x plus y squared equals to sine y. 4 minutes left for class, and then another 35 after that.
It is.
All right. We start with the chain rule, right? Right? Yeah. So 1 over 2 square root of x plus y squared times the derivative of the inside, which is derivative of x is 1, plus 2y, and this is where dy dx goes, equal to cosine y dy dx. Nice. All right. So now we have to distribute, separate the terms, and then put dy dx terms on a pile. So we have 1 over 2 square root of x plus y squared plus y over square root of x plus y squared dy dx equals to cosine y dy dx. Note that that 2 canceled, right, as you distribute. So it doesn't cancel for the first term, it cancels for the second term. I'm going to put the arrows so we know what happened there, right? So on the second arrow, the 2 cancels. Now we'll shovel the terms. Eventually you will be able to write the final answer just from here, from this line, if you do this enough, because this term has to go this way, so you pick up a minus, and then you know you have to divide by this minus that. So this one goes there with a minus, this one goes here with a minus, and then just divide. You can write immediately. But that kind of algebra at the beginning, right, step by step, so we don't miss anything. Oh, it's faster if I just move this term to the left, to the right. Factor out dy dx. And dy dx is equal to now we don't like double fractions, right? So we're going to multiply top and bottom by 2 square root of x plus y squared to get rid of all denominators. So on top everything cancels, right? It's just 1. On the bottom we get 2 cosine y square root of x plus y squared minus 2y, because the square roots cancel. You could factor 2, but nah. That's it. Now imagine the second derivative. Take another 25 minutes. Because, I mean, Sunday is coming. What else are you going to do? Get up in the morning, stretch, and do 2 implicit differentiation second derivative problems, and you're ready for bed. That's Sunday. Look at that. 3 minutes left. And then another 25 after that. Tangent line? So this is how tangent line problems look like. All the way on the bottom left, you have those two shapes. So we have the sideways ellipse, which is problem 25. Problem 26 is whatever that thing is. But you see the equations. And you can find the slopes of the tangent lines through implicit differentiation. We also have these problems for tangent lines. Any of these functions. No, not functions, sorry. Relations. They're not functions. You can find a tangent line for every single one of these. Yes. 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 Do you want me to? I wasn't waiting for that. It's like, can you? I said, I can. Ah, there we go. I just did. Hmm? Wait for the project. Four. 2 months to do it. I figured that much. As soon as we're done with 3.9. It's gonna be epic. Oh, you're welcome. Anytime. Tangent line problem. Something simple. X cubed plus y cubed is equal to 2xy at 1, 1. This is problem 28. So find the equation of the tangent line. And you have the relation x cubed plus y cubed equals to 2xy. If you have it, who's done? Check behind you, see if you have the same. And then compare the steps if it's not the same. And if you can still figure it out, just take it outside. Yeah. And then work that out browse much quicker than shoveling more X's and Y's around. Okay. Three lines. You've done one. This is what makes me happy. The learning.
Oh, here you gotta divide by here now. Remove this one. So you gotta dy dx.
So next Saturday we'll be done with the material for the next exam. We only have 2 sections left, 3, 9. No, that's next month. November 12th.
I understand what you're talking about. If it's like 2x and
Let's talk about this together. Derivative of x cubed is 3x squared plus derivative of y cubed is 3y squared dy dx. Awesome. Equals to the product rule. Product rule says what? Copy the first, 2x times derivative of the second. Derivative of y is 1 dy dx plus copy y, and derivative of x is 2, so 2y. Now, you could go and solve for dy dx by shoveling terms and factoring and all of that stuff, which is going to take about 3 steps. But since we don't care about what the equation is, we only want to calculate the slope because we have 1, 1. Just plug everything immediately without simplifying it or using any algebra. Because so now plug 1, 1. And what we get? We get 3 plus 3m. Because dy dx becomes m. Equals to 2m plus 2. M is negative 1. All cool. I see all the smiling faces, which means you guys got this. You got this negative 1.
can you put dy dx and dx together and make sense? I don't understand why you use product rules and all that stuff.
Because it's 2 different things. There's a times over here, right? So if there is times, there is a product rule.
You're putting dy dx to everything right now to all the equation.
No, I didn't.
Wait, d
Copy the first. Derivative of the second. Derivative of y is 1. But because I'm taking derivative in respect to x, dy dx follows. And then plus. We'll do it after this. All right, we'll sit down. And now we have the slope of negative 1, y equal mx plus b, which means 1 is equal to negative 1 times 1 plus b. B is 2. And the line is y equals negative x plus 2. Green? One more problem and we're done. Two problems? No. I paid till 1:15 and that's what I'm leaving. Okay. All right. Let's see what we can find. Let's do some more chapter 4 prep, huh? Tangent line for problem 50. They just ask for slope, but you can do the algebra part of figuring out B in 5 seconds. So tangent line, they give this wonderful, look at this, y x to the 5/2 plus x to the 3/2 times y is equal to 12, and they give you a 0.41. So x y to the 5/2 plus x to the 3/2 times y equals to 12. The point is 4, 1. So what do we have here? Two product rules. Very good. There are two product rules here. And yeah. So there's going to be lab time next time, guys. For like an hour, 2 hours, 3 hours, whatever. Make sure you have most or all of the lab completed. Most of it, not all. Most. Oh, it's 70%. All right. We have 4 minutes left, so let's go with this. We start with the product rule. Copy first. Derivative of the second would be 5/2 y to the 3/2 times dy dx, because we took derivative of y, plus copy y to the 5/2 times derivative of x is 1. Plus, now that's that plus, derivative of, so copy the first one. Derivative of y is 1, so we just have dy dx there. Plus, copy y, and derivative of x to the 3/2 is 3/2 x to the 1/2, and everything is equal to 0. As I mentioned earlier, it's easier if you just plug everything in now rather than solving for dy dx and wasting time, because when you're looking for tangent line, no one cares what dy dx actually is. You will just replace everything immediately and be done as quickly as possible. So x is 4 times 5/2, and then you have y, which is 1 to 3/2, so that's still 1, and dy dx becomes m plus 1 plus, and now we have 3/2 to the 4th. Square root of 4 is 2, cubed is 8m, plus y is 1, don't worry about that. X to a half with square root of 4 is 2, cancels 2, so 3 equals 0. So the first term, 4 and 2 cancels, we get 10m, plus 8m is 18m, plus 4 is equal to 0, m is equal negative 2 over 9. Yes? And the rest should not be an issue. 1 is equal to negative 2 over 9 times 4 plus b, which is 1 is equal to negative 8 over 9 plus b, from where b is equal to 17 over 9. And we have our tangent line. Y equals negative 2 over 9x plus 17 over 9. Look at that. 35 seconds before time. Professional. All right, that's it for this one.